Bismillahirrahmanirrahim. Welcome back to our course on deep learning for computer vision. Let's jump to our lecture and see what we can do. Our today lecture will be entitled, as you see here, Image and Video Acquisition. We'll talk about image and video acquisition devices and see what are the variations of these devices and applications. The titles or the guidelines for this session will be, as you see here, we'll have a look on digital image cameras, on image scanners, digital displays, printers, and in between we'll see many demos regarding all these topics. So let's start with the first title, digital image acquisition. What we mean by image acquisition? In fact, the computers cannot process actually digital data because they need specifically the data to be acquired or applied to the computers in a digital form. However, images are naturally accepted or afforded in analog forms because we are living in an analog or a continuous world, and what we see, what we talk, what we can sense is naturally in analog form. Now, as a prerequisite, we need for digital image processing, we need to convert these analog signals or analog inputs into digital form. This includes, for sure, images and videos. In our industrial and daily life techniques and devices, we may find two types of image acquisition devices like the scanners and cameras. Now, the scanners and cameras are used to acquire images and convert it into a digital form to be used further for our applications. The digital cameras, this is the first type of the image acquisition devices. Now, the image, what is the digital camera? It's a device that captures images and utilizes image by a sensor and utilize this for further applications. Now, in other words, the digital camera is a transducer that converts the light or the light incident to the camera into an electric version and converts the visible light as an electronic signal. In fact, these cameras do not use photochemical film. As you know, in cameras, in the old-fashioned cameras or in cameras that we can see in maybe 20 or 30 years ago, you can see there we have photochemical films, and you have the negative, then you convert this negative into its opposite version and print it on a paper to get your image. Instead, in this case, we are going to convert the light incident by the original scene, or what we can see, into an electrical or electronic signal that is recorded either on an internal memory, or it can be sent or transmitted remotely to another connected device in a remote sensing application. Now we can distinguish here three main types of digital cameras: the charge-cable devices, CCDs, CMOS cameras. These two types are very close to each other, the CCDs and CMOS cameras. The third type, which is a little bit differs from the first two types, is the charge injection devices, the CIDs. Let's go and jump and see what we can find regarding these types. Now, in case of the CCD cameras, the CCD camera is a device that records the image electronically. So it looks like another digital image, another digital camera. In the CCD chip, actually, mainly we have inside this camera a chip, as you see here. And this chip, so maybe you can see here different types or different CCD sensors. These types of, let's say, chips or CCD cameras can be manufactured on a light-sensitive crystalline silicon chip. So it will be a silicon chip, that is light sensitive, that is sensitive to light, and contains two-dimensional array of MOS capacitors. In general, either we have CCD or CMOS capacitors. We are going to implement a sort of capacitors that are ordered in two-dimensional array or in a matrix. And when you expose this CCD front part to the light, it will be charged, or it will have some charge produced by the light incident to it. The larger the light, or the stronger the light, the more powerful the light, the higher the photon generated charges or electrons will be on this chip, or on this. For sure, we are talking about the chip itself and about the capacitors that are ordered inside this chip. Here we can distinguish three types of cameras. Full frame CCD depends on the scanning type or on the reading process. We can distinguish the full frame CCD, the frame transfer CCD, and the interline CCD. Let's go and see what are these types. And okay, so as you see here, the basic idea or basic operation behind the CCD camera, that we have this chip, as you see here, and it is very clear that when we have light incident to the chip, there will be produced, we call it a potential well that contains electrons, and these electrons will be captured, or will be, let's say, gathered together in a potential well, a small packet or a pocket maybe, and it will still there until we apply positive voltage to the gate, where this charge will be, or this potential well charges will be transferred to another place. It could be the reading process in this case. Now, it's a good question, what about RGB? Now, where is the colors in here? In fact, you have to understand this this way. This location, or this potential well, can be decomposed, or can be consisted of three sub-potential wells, one for the red, one for the green, and one for the blue. And this means that we have a more complicated design and manufacturing tools to build such type of, let's say, cameras. We have mainly, as we just said before, that we have here three types of CCD cameras. Here, the first one is the full frame. In the full frame, this is the chip. Let's have a look at the chip. Okay, this is our chip here, and this is the full frame that we mean by the chip itself, the front of the that is exposed to the light. And when light comes here, it will be charged with by the photons into, and the charge will be converted into electrical or electrons. These electrons will be combined in potential wells at every charge location, every CMOS location. As you see here, we have here a matrix of pixels. Okay. So next, after that, we are going to shutter the CCD camera. The shuttering means that we are going to close, or to shutter the light from being exposed to the camera again. In this case, the charge is already given on the frame, or on this CCD chip, and the reading process starts as you from down here. Let's go and show you this. Let's remove all these things here. And the reading process will start here by shifting down pixel by pixel, or the charge of the potential well one by one, and serially it will read these pixels in this shuttered, or always shuttered row. It could be a column also, and the reading out will be applied by reading the value, or the intensity of the charge for every of these potential wells. After finishing the reading process, we go back again and expose our full frame to light and then shutter it out, shutter it down, and continue our process until we finish working with these images. So the idea here that the read process may take, it's clear and cut that it may take out of time for reading because it will read the whole image. Is there any other technique? Yes. This is the frame transfer. In this case, half of the chip will be covered, as you see here. Here, the CCD chip that will be always exposed to light and shuttered is this part, while this part will be not applied for the light exposure, and it is called as masked storage array. In this case, after shuttering, after exposing this part, which is the image array, to light, it will be charged by electrons that transduces, as we know, the light into electric charges. Next, very quickly, we're going to shift down, as you see here, all the image array into the masked storage array. Then, after that, the reading process will start below here. We'll start at this place, as you see here, okay? And the process will be continued until we finish reading all the masked area. And meanwhile, as it's clear, meanwhile, while we are going to read the charges that are below or behind the masked storage array, in this during this time, we are going to apply the light or expose the image array to light. So it's clear that when we compare it with this one, the time processing here will be shorter, and it may be reduced or dropped to, let's say, half of its total time required for processing. Okay. Let's go now to the third type. Here, interline CCD. Interline. So if you see here, we have one column is allowed to be in the image array. The next column will be masked and not applied to light in general. Now, when we read this, when we expose light, expose the image or the CCD chip to light, as you see here, the exposure will affect only the image array, which is in the row of columns, as you see here, while the masked region, where we have the other columns that are not allowed or are masked and not allowed to be exposed by light. So after shuttering the image array, we'll go and shift all these pixel values or the charges down to the register, the serial register or the readout process. So we just need to shift by one column. Let's have a look deeper in this case, or maybe we need to zoom. Let's have a look on this. Okay. Here, suppose that this is the image CCD camera. This part, let's see this one. Now, this one will be, this row, column will be masked. This one is also. Now, suppose that we have light here. The charges are concentrated by the light incident to this chip. Okay. Next, after shuttering, these pixels will be shifted to the masked area. As here, we are going to shift by one pixel only, while in the second type, we need to shift by half the array, which is about 50%. This will take some time. Now, after doing that, we are going to read out from these places. These also is shuttered, and the readout will be done during the next exposure, and this will give us higher speed in reading the image values, or the image pixel values, or let's say the potential well values that are charged that are accumulated in the CMOS charged capacitor. So the speed here is higher than the second type, and for sure is higher than the in the first type. Okay. So these types are now are available in all cameras, in all mobile phones, in computers, and its price depends on the resolution and the speed in processing, etc. Now let's go to the CID cameras. What are the CID cameras? If you look at here at this video, or let's see on this image, here every potential well, as you can see here, contains a capacitor that is connected in a row and a column scan. So when dealing with, in this case, when exposing this camera to, let's say, to the light, it will be charged, as you see here. It will be charged with the proper value of electron of charge or photoelectron power or intensity. Next, the readout process can be done partially or totally. So what do we mean by that? The first type, as you see here, is the non-destructive readout process. Now, in this case, when we can just apply, as you can read here, then when after applying the pixels and applying the exposure time, we keep the voltage on the capacitors in this case to be always positive. In this case, the charge will be accumulated and preserved at this location, for example, and no change will be done. We read this value by applying to a specific circuit or a device, and if we are satisfied with the values, we either keep it, we can change it, we can apply zero voltage to discharge this potential well. What is the difference between CID and CCD? In the CCD case, we can't apply a partial discharging. We can just do total discharge. In this case, we are applying discharge on every potential well, and this will give us a complicated processing step. Not very complicated, but it's more complex than what we have seen in CCDs. In the destructive readout, in the second type here, in the destructive readout here, okay, we are going to apply a voltage which is set to 0, and this will lead to for example, this potential well is not proper for us. We can just remove the charged or the charges or the electrons here that were caused by the exposure, and let it set to 0 and remove all the charge by reading it out, by replacing its value or by removing its value. Now, what this gives us in this case, in destructive readout, we can read the whole image, and as in CCDs, and read out all these values in the pixel sites, and read it out and set again to make it set to 0, and prepare it for the next, let's say, exposure. Now, these cameras are very specialized because we can wait for a long time, waiting for the charge to be accumulated and to get a specific or maybe an acceptable level that is for us a pleasant view. It may be for in astronomy, in industry, etc. Sometimes we may get some sort of smearing or some extra light in some locations, for example, at this location. Now we can correct this and remove the charges, can remove the charge here and set it to 0 and prepare it to the next exposure, and exposure may extend for a long time. This is the difference between the non-destructive and destructive readout. That is a good property and a very an amazing property for the CIDs that was not available and not possible in case of CCD cameras. Now, this is a good maybe tutorial to have it as an example on CCD cameras. For in this case, we have the readout process is done on in a column wise, and this is also available. Then the output is read out by the amplifiers that will be sent further for processing and for storing maybe or transmitting on to another places. As you see here, if you look at the pixel wells or the potential wells, you see that these wells are when the light is incident from the light is here incident. We can see that as you see just a minute. So this is the shifting process that can be done. We just shifted by 1 pixel. Then the readout is done serially, as you see here, 1 by 1, and this will give us how the operation is done. And the process is repeated step by step until we finish dealing with all these potential wells during the shutter time and waiting for the next exposure to light again. Here, another image. What is the difference here? The difference is in the potential well. It's not a charge coupled device, it's a CMOS capacitor. I see that it looks like a photodiode or a MOS capacitor that can be used simply instead of the charge coupled device. Instead of charge coupling, it will be CMOS coupling. And at the potential side, we have, at the pixel side, we have a potential, instead of the potential well, we have a sort of CMOS capacitor that can be used for charging and discharging. When applied to light, it accumulates the charge. Then it will be let's say discharged through the filters and the accompanying circuitry in the CMOS cameras. Okay. What is the difference between CCDs and CIDs? As we have seen, there's an important difference in the speed in the processing and in the objective or the goal for which these cameras were designed. Let's have another look here. In case of the CCDs, we may be dealing with what we call it by blooming and smearing. What we mean by this, when we expose the CCD camera to concentrated non-uniform light, this will cause that the light reflected from these objects will be, it looks as being spilled from over the saturated elements to surrounding pixels. And this will cause some, when we read out this piece of image or this part of the image or these pixel sites, this will lead to some annoying effect as noise, and we call it as blooming and smearing. In CIDs, this effect is not can be easily overcome, and this can call it anti-blooming performance that is done by discharging these parts before reading out for the final reading out process. CIDs are used effectively for very accurate and very advanced applications like missile tracking, industrial applications like semiconductor pattern recognition, factory inspection, etc. All these advanced applications require a good camera to be used in as a piece of these, as a part of these systems. Here we have an example on the blooming effect in CCDs, and as here the same, this is inspection at industry, where we have a board, and we after exposing, we may be using here a flash, and you see that the quality is not very clear, while when you look at the other part, as here in this image, when you look here, for example, at this part, you can see the number of the IC, and while here you cannot even read what is behind. And some part of the image, maybe a displace or this place, you can see here that these details are very clear, while in the CCDs or in the CCD image are not well seen. This is one of the benefits that CID. Moreover, the CID can accomplish good output image quality, and it avoids the smearing and blooming effects that may occur in case of using the CCDs. Someone may ask about the thermal cameras. What are the thermal cameras? The thermal cameras are cameras that are used to visualize and see the thermal radiation in the surrounding or in the object in front of the camera. They have a lot of applications. For example, in our field, we can use it in inspection of PV panels where we have some faults or problems with the cells inside the PV panel. And let's have a look on this piece of video, and I hope that it will be enjoyable for you. Of course, here you have, as you can see here, a worker having a mobile phone in his hand, and this piece of material, or maybe the dongle here that he is holding, is a thermal transducer or converter to convert the light. It contains a sensor as a thermal camera inside it, and when we attach it to our mobile, and look here, as you see here, as when we go and apply this application, of course, that's its own, let's say, software. And when he is trying to expose or to look at the PV panels, as here the PV panels are very clear and cut, they are very clean, and you don't believe that you have some problems here. When we go further and look at this image that was captured by this device, you can see here that a part of this is the energy, or let's say the temperature of the PV panel surface. As you see that we have here, for example, for this cell, the cell is very bright, and it means that it has a high temperature, while this one is operating very well, and it has no problems. While in this part here, as you see, this cell, maybe this one is problematic. Here it could be more or less good. So this camera converts the thermal radiation into the visual spectrum and can be used for such applications. It has a lot of applications in scientific and in industry, in military applications, and it looks one of the attracting, let's say, fields of applications these days. Let's go to the second type of image acquisition devices, the scanners. What is a scanner? It's an electronic device that converts the image into a digital form. Again, it looks like a camera. However, here, what we are going to deal with, as here in this image, this cartoon, that it requires to have the image on a paper, or maybe on a very thin, maybe film or material, so it can be converted from this paper or from this image using the scanner into a digital form. Different types of scanners. I'm not going to take a lot of time to talk about these. I think it's very familiar for you. The handheld scanner, it looks like an enlarged mouse, and it can scan images from documents with a DPI resolution of between 100 and 400. It may be more or less according or depending on the company that manufactures these devices. The flatbed scanners, they are very familiar, and they are always attached to the computers, and here the resolution will be up to maybe a couple of 1000 dpi, which is very high. Other specialized scanners that are used, slide scanners, they can be used for reading from thin films, the negative thin films. Maybe you are not familiar or not dealing with these types of scanners, but they are usually actually working well these days, especially in industry applications and in printing applications, large scale printing. So you may get a resolution up to 6,000 by 4,000, maybe more, and many magazines are using these scanners. We have also drum scanners for large size printing. This can be found in industry, and their resolution may appear to be more than 6,000 by 4,000, higher than the slide scanners. However, it has its own applications. Of course, we can see also other scanners like the fingerprint scanner, the iris scanner, the barcode scanner, or the QR code scanner, etc. All these are now very public, and most of us are dealing with these with such types of scanners. We so far have seen digital cameras that convert the incident light or the photons into an electrical version, and it records the image or the video into a digital form on a computer for recording, for saving, maybe for transmitting remotely to another site. Now we need to have another operation, which is the opposite one, where we have a digital file and want to display this file and see the content of what we have inside the file. This file. This answers for what we call it the digital image displays. So the devices in this case, or the displays, are used to display or to show the images on a screen or maybe on other devices. Now, the devices used to display and show images are of two types: permanent displays that produce a hard copy image on a paper, film, or other device or medium, and the volatile displays that produce a temporary image on a display screen. So we have two types. The first type is the permanent displays. The permanent displays. Okay, this one. What is the permanent? It means that you cannot change it maybe after displaying the image. So this will be as a paper, maybe transparency, etc. While in the other type, it's the volatile display. Here, what we mean by the volatile, that when you remove or shut down the device, like the mobile or the computer or the TV screen, the image will disappear. And this is why we call it as a volatile display, because it produces a temporary image on the screen. Okay. Here we may recognize different types. For volatile displays, we may have the cathode ray tube, CRTs, old-fashioned volatile displays, LCD type displays, and MCD type displays. These are the modern types of displays that are usually in these days we can buy it and deal with it in the market. The other type of displays is the permanent displays. Here we have different types of printers, mainly inkjet printers, laser printers, thermal wax printers, dye sublimation printers, etc. All these types of displays are mainly the printers. I'll talk about these types of displays very quickly. The plasma display is an old one for digital display. Mainly it uses the xenon or neon gas, and in this case, when you apply the electric signal or voltage to the gas, it will be between the two plates of the glass. The plasma starts to lighten, or to, let's say, to shine, and the shining will be converted and captured by the front side of the device, and will produce light. This type of displays, which is the plasma, is very expensive. It consumes a lot of electric power, and it has been, we can say that it has been removed from the market, or there's very you can really find such displays, and they are very old these days. The LCD is the liquid crystal displays. You can find it in calculators and some devices. However, it has 3 subpixels in case of the display itself. And the main idea is that we use, instead of the plasma, we use a liquid crystal that is polarized and starts shining when applying a voltage according to the value of the current passing the crystallized liquid, and it will again shine and produce light on its front side. The OLEDs, mainly LEDs, light emitting diodes. Here we are using the organic because they are very light. They are not very expensive, and they are very commonly used in current in nowadays displays. And these display, as you see here, the construction of the device. However, what I want you to remember is that we are going to use a sort of LED, because the LED, light emitting diode, it emits light when a current or a voltage applied to the LED itself. So when by varying the current or the voltage applied to the LED, it will shine, and it will emit light that will be also varying accordingly. So these devices are now very common, very popular, and very spread all over the world, and their price is going lower and lower, and are available for all in many countries. The other type of displays is the permanent displays, are the printers. Now, what is a printer? It's an electronic device that converts the image into a digital form. So you can, in this case, convert the image file from the memory or from the storage device into a digital form that can usually stored in a specific file format, usually on a paper or maybe a transparency or any other medium. We can recognize different types of printers. Inkjet printers. We can also see other types are the thermal printers. Let's have a look very quickly on these types of printers. First type is the liquid inkjet printer. This is also an old-fashioned printer. Nowadays, are not using a lot of these types of printers. The main idea is that we have here the cartridge. Okay, here we have the cartridge or the ink that contains CMYK, and when we apply the voltage from some source or the passing current into this printer, from, let's say, from here, you can this will cause the what we call it, the cartridge or the piezoelectric crystals to spray, or to spray droplets of ink on the paper, and the intensity of the spray will be depending upon, or they will be depending on the current applied to the cartridge. And we have here three sub cartridges having CMY, and we have another cartridge for black and white printing. So we have two reservoirs that have that are storing the liquid ink. In fact, these printers are very cheap, and nowadays they are not very attractive for people. When we want a more and more good quality or higher quality, we look for better printers to buy and to get images through it. The other type is the ink, the solid inkjet. The same thing, but instead of having the ink in the form of a liquid, it is converted into a sort of color sticks or molten ink. So we have like the toothpaste, you can see. And when the same principle of applying the current or the voltage, and when pressing when applying this voltage, these cartridges will be somehow pressed and produce ink, molten ink on the paper, and will cause the image to be appearing on the paper. The other type of printers, not the inkjet printers, the thermal wax printers, instead of having the cartridge here, as you see, instead of having the cartridge in the form of what we call it the ink cartridge, here we have a sort of liquefied wax. So we have a tape. On this tape we have some colors, CMY and KMB. And when we apply heat according to the current applied from the file or from the source, the computer, it will press on the tape, and this tape will produce molten wax on the paper. So of course, in this case, the paper will be covered by wax, and the quality of the image will be shiny and very pleasant for your view. Let's go now to the laser printers. In the case of laser printers, we have again toner cartridges. These toner cartridges are of specialized material. The main idea is in the scanning process. When we apply, we are using the laser to scan the paper, and we drop ink on the paper and start burning by the laser scanner, or by the laser, let's say, beam on the paper, and burning the paper to get the ink sticked on the paper. And by having CMY and K for sure for black and white printing, we will get a pleasant and a good output that is usually in these days used everywhere. When you go to the bookshops, and when you want to get xerocopy, you can find such good and beautiful images produced by the laser printers for grayscale and for color images, for sure. So that's all talk regarding this topic. I hope that it will be useful for you, and see you soon on the next lecture. Assalamu alaikum.